What happens when we have an oscillating charge between 2 points, a dynamic dipole? Hi, this is Jonathan Gardner covering Griffith's Introduction to Electrodynamics, 2nd edition. I'm on section 9.1.2, electric dipole radiation. In this section, we're going to look at a dynamic dipole, figure out its scalar and vector potentials, and then calculate the E and B fields. We're going to make use of the retarded potential in our calculations, and once we get the E and B fields, then we'll look at the Poynting vector. Finally, we'll make some observations about the color of the sky. Buckle up. This one's going to be a bumpy ride. In this example, we have two charges a distance s apart. Let's see if I can get my mouse working here. Where's my mouse? There it is. All right, S. So S points from the negative charge to the positive charge. We're going to find the fields at a point P, which is actually very far away from these two charges. The vector R points from the center of the dipole to the point P, while curly R plus points from the positive charge and curly R minus points from the negative charge, or rather the top charge and the bottom charge. The angle theta here describes the angle R makes with the horizontal. We'll be working in spherical coordinates for the most part. Since we want to emulate a dipole, we'll keep the total charge at 0. If one side has a charge q, the other side has negative q. If we didn't do this, the net charge would dominate the equations and we lose the subtlety of the dipole. The charges will change over time. You could think of it in a few ways. You could pretend the two charges are attached to imaginary springs, not unlike a hydrogen atom. This is difficult because we haven't covered accelerating charges yet. Alternatively, we could imagine that there is a current flowing between them. Either way, we'll consider the charge to be changing at a frequency omega. Right, there's my mouse. There it is. In order to solve the equations that will follow, we're going to use some approximations. We're only interested in the region far away from the dipole. In that region, we can apply these approximations. First, let's realize that the distance r is going to be much greater than s. That's handled by this approximation at the top there. But also, we're going to consider that the speed of light is much faster than the speed at which the charges will flow back and forth. This means that any waves we generate will have wavelengths much larger than s. So that's represented by c over omega being much larger than s over here. C over omega, of course, being the same as the wavelength. And but compared to r, the wavelength will be quite small. Of course, if you raised or lowered the frequency sufficiently, some of these approximations won't work very well, so we're not going to do that. Let's look at the equations for q and the dipole moment p. The formula for the charge over time is simply the cosine of omega t times some maximum q naught. Keep in mind that the bottom charge is opposite the top charge. So this is the charge on the top charge. The bottom charge would be negative this, of course. The dipole moment of such an arrangement is easily calculated. It's just qs. That gives us a dipole moment maximum p naught. Put it all together when we have the simple equation. The dipole moment at time t is p naught times cosine of the frequency omega times time t, and it points in the k hat direction, aligned with s, so vertically. At this point, we can calculate the scalar potential v. We're going to use the retarded time t prime. That's simply the time minus how long it takes for light to travel from the charges. The vectors curly r plus and curly r minus represent the distance from the top charge and the bottom charge to the point in question. Now we can write down the retarded potential. We just substitute in the retarded time for the time we're talking about at the source and use the basic electric potential for a point charge equation. This equation looks complicated, but it's really not. The retarded electric potential of a charge is simply 1 over 4 pi epsilon naught times the charge seen divided by the distance. This is nice, but we can make things simpler. Let's translate curly r's to r and theta. First, we use the law of cosines. Note that for r curly r minus, the angle we should use over here in this picture, the angle down here that we're going to use, or actually this angle right here, is just a pi minus theta. Well, cosine of pi minus theta is just negative cosine theta, as you might recall from your trigonometric identities. So we first pull out the factor of r from the square root. So we have r, so it comes out of here as r squared. There's only one r on top, so now there's an r on bottom. And down here we have an r squared in the denominator. Note that s over r is practically 0 since r is much greater than s. But if we set both of these terms to 0, we'd be left with just r, which is not what we want. So we're going to ditch this right-hand term and keep this middle term. Finally, we can take the binomial expansion of this, and this becomes r minus or plus s over 2 cosine theta. We're not going to use the rest of the terms, just those first two terms is enough. let's calculate 1 over curly r plus or minus. Again, we pull out the r, we ignore the s over r squared term, and this time it's a binomial expansion of the negative 1/2 power, so we get plus or minus instead of minus or plus. Before we tackle the entire equation, let's look at the cosine part. Plugging in curly r plus or minus, we get a bit of a mess. But we can apply the trigonometric identity that cosine of a plus b is equal to cosine a cosine b minus sine a sine b. So cosine of this plus that is cosine of this cosine of that minus sine of this sine of that. And cosine of this minus that is cosine of this cosine of that plus sine of this sine of that. Now we can look at this term omega s over 2c that appears in both this cosine and that sine. Keeping in mind that this is just s over lambda, and we know that s is much smaller than lambda, so this is basically 0. It's not exactly 0, but it's close. Well, cosine of something close to 0 is just 1, so we replace this with 1, but sine of something close to 0 is the expression itself, so this becomes omega s over 2c cosine theta. And so we're left with this. We have cosine omega t minus rc minus or plus omega s over 2c cosine theta times sine omega t minus rc. We can now rewrite the retarded potential altogether. We've eliminated the curly r plus or minus, and we've reduced everything down to equations involving just r, theta, and t. Excuse me. Substituting those in, you get what appears to be a mess. However, you should be able to see some of these terms disappearing. So we have, from this first term, we have this times that. The left-hand side is coming from the top of the denominator. The bottom curly r plus is this thing over here. And we're subtracting this, which is cosine omega t plus s omega over 2c cosine theta sine omega t minus rc, and of course in the denominator, which is 1 over r minus s over 2r squared cosine theta. Okay, so let's look at these terms. So this term, this cosine omega t minus rc, is going to multiply with this term, and it's going to multiply down here as well. But on this top side, it's positive, and on this bottom side, it's negative. So this term, the cosine and the 1 over r cross term, is going to disappear. We can also see that this term, negative s omega 2c plus that, and then we have, well, this negative sign comes in, so we have negative s over 2c times negative that. So here we also have this term cross multiplied, also cancels itself out and disappears. However, when we take this term and multiply it by this s over 2r squared cosine theta term, we see that this is this plus that minus this times minus that, so we have two positives. So 2 cosine omega t to rs cosine theta. Oh, let's go back. Also, this term right here, the s omega 2c cosine theta sine omega term, sine omega t minus rc term, multiplied by the 1 over r term, over here it's negative times that, and it's a negative times that, so we get minus 2 of those terms. Okay. Simplifying, we have a 2 in the top, and we have a 2 on the bottom, a 2 on the top, and a 2 on the bottom, so those disappear. We pull out the factor 1 over r for here, and we're left with the cosine theta over r. This cosine theta, and there's an extra r over there. Cosine omega t minus rc. And we have omega c, omega over c, and we have cosine theta over an r. It comes from there. Sine omega t minus rc. I'm writing these out in this way because it's going to be a pattern that we're going to see over and over again. This middle term here depends solely on the geometry of where point P resides, and this term depends on the distance from the center and the time, and of course the frequency. And here's a factor that scales it accordingly. Over here we have this extra 1 over r. Something's going to happen to this later. We're going to find out what. Okay. All right. So we're left with this mess, this glorious mess. Q naught s becomes P naught, 4 pi epsilon naught, cosine theta over r, both of the terms have that, and we have 1 over r cosine omega t minus rc minus omega over c sine omega t minus rc. So let's poke at this equation for a bit. If we take omega to be 0, so if we substitute in omega 0, this cosine terms become 1, this becomes 0, and we are left with P naught 4 pi epsilon P naught over 4 pi epsilon naught cosine theta over r squared, which is what we expect to see in the static case. But if we take r to be much bigger than the ratio c over, so r is much greater than c over omega, which is the same as lambda, then this term is much more closer to 0 than this term ever will be. And so we can just drop the cosine term, and we're left with this equation in the end. So v of r, theta, and t is equal to negative, from this negative, p naught omega over 4 pi epsilon naught c cosine theta over r sine omega t minus rc. So there we go. We've taken that complicated equation, reduced it down to something simple by taking a few approximations and noticing which terms cancel. All right, let's take a look at the potential really quick. First, we notice that according to the geometry, we have cosine theta. So that means that near the poles, the potential is the greatest magnitude, either positive or negative. We also notice that it decays based on 1 over r, the further you get away from the center. And we also notice that we have this omega term and this phase that depends on the distance from the origin. So that's what you would expect to see of a wave emitting from some central point. All right. So let's turn our attention now to the vector potential A. Calculating the current is trivial. It's just the time derivative of the charge over time. Calculating the vector potential involves the integral of all the bits of wire along the path from the bottom charge to the top. I'm not going to lie to you, this was a very complicated integral to solve, and I wasn't able to solve it directly, but I did take advantage of some key assumptions, and I ended up with what Griffiths ends up in the books, which he says basically just take what the field should be at the center and apply that all across the disk. So he just basically changes this entire thing into sine of omega t minus regular r over c. And you end up with this equation that has two components. The first is negative mu naught p naught omega over 4 pi. We have cosine theta over r, sine omega t minus rc in the r hat direction. And then we also have a component that is in the theta hat direction, mu naught p naught omega over 4 pi, sine theta over r, sine omega t minus rc. Okay. Notice that we converted from k hat to spherical coordinates. K hat gives us the cosine theta r hat, sine theta theta hat. So finally, we're going to compute the E field, and in order to do that, we need the gradient of the V and the time derivative of the A field. In spherical coordinates, the gradient of V is, we already calculated this, negative p naught omega over 4 pi epsilon naught c, cosine theta over r, sine omega t minus rc. And so if we take the gradient of that, we have to take the derivative, the partial derivative of V with respect to r in the r hat direction, and 1 over r times the partial derivative of V with respect to theta in the theta hat direction. Whew, that's a mouthful. So from the r direction, we have the partial derivative with respect to r. There's two terms that has the r in it. So we pull out all of this stuff. The first is this term, which we get an extra minus 1 over r. And the second is this term, which we get an omega c coming from the factors of r, a minus omega over c, and this sign becomes a cosine. So that's the r hat direction. And in the theta hat direction, we start with a factor of 1 over r. And the only term with the theta is the cosine, which just becomes sine. So we have this all together. Notice also that we have a 1 over r here, and we have a 1 over r here, but there's no 1 over r here. So since r is much greater than c over omega, again, these terms with the 1 over r will become 0, and we just focus on this one term right here. And so the resulting gradient of the scalar potential V is p naught omega squared over 4 pi epsilon naught c squared cosine theta over r cosine omega t minus rc r hat. And that gets us the gradient of the V, but that doesn't give us the time derivative of the A field. For that, let's look back at the A vector. This is negative mu naught p naught omega over 4 pi cosine theta over r sine omega t minus rc r hat plus mu naught p naught omega 4 pi sine theta over r sine omega t minus rc in the theta hat direction. So the time derivative appears in this sign and in this sign, and they just become cosine, and we get an extra factor of omega on both accounts. So we have negative mu naught p naught omega squared over 4 pi cosine theta over r cosine omega t minus rc r hat plus mu naught p naught omega squared over 4 pi sine theta over r cosine omega t minus rc theta hat. Pretty simple stuff. When we combine the two together, it looks like this. So from the gradient of the V field, we have, if I can find it really quick, I'm going to flip back really, very quickly here. So we had something in the r hat direction. Okay, there we go. This is from the gradient of the V field, and this comes from, these two terms come from the time derivative of the A field. Now, this epsilon naught, we can actually convert that, epsilon naught c squared, we can convert that just to mu naught. So if we remember that 1 over c squared equals mu naught epsilon naught. So we have negative mu naught p naught omega squared over 4 pi cosine theta over r cosine omega t minus rc in the r hat direction plus mu naught p naught omega squared over 4 pi and we have this factor of 1 over r of cosine omega t minus rc, and then we also have a cosine theta over here. So there's a 1 over r, cosine theta over r in the r hat direction. This one's minus, this one comes down here like this one's minus, this one's plus, and we're left over with this theta hat term. So the gradient of the v field cancels out the r component of the time derivative of the a field exactly. And so we're left with, I have an extra line here, don't I? I do. Oh well. We're left with the E field is equal to negative mu naught p naught omega squared over 4 pi sine theta over r cosine omega t minus rc in the theta hat direction. Let's take a moment to analyze that. Theta hat, if you're standing on the surface of the Earth, and the Earth is a sphere, theta hat will always point towards the North Pole, no matter where you're at. Well, at the South Pole it kind of points anywhere but where you're at. Anyway, but it's saying that the electric field is pointing, well, opposite the North Pole, but it's going to vary back and forth between positive and negative. And it's going to be maximized around the equator and minimized at 0 at the poles, where theta equals 0 and theta equals 90 degrees. To calculate the magnetic field B, we only need the curl of A. Luckily, there are only r's and thetas. We don't have any phi's in here, and so it's tremendously easy. We have the theta, the partial derivative of the r component of A with respect to theta, in two places, here and here. And we also have the partial derivative with respect to r of r times the theta component of the A field. Now, we're going to take advantage of the same kind of simplifications we've used before. When you take the theta hat derivative of, the partial derivative with respect to theta of the r component, then it's just going to change this cosine into a negative sign. Okay. However, there's still going to be this 1 over r term. But when you take r times the theta component, this r and that r cancel. And so when you take the derivative with respect to r of that, there is no r. There is no 1 over r term except for from this factor. But this also has a factor of r. So basically this one has r squared, 1 over r squared. This one has 1 over r squared. And this is the only term that only has one r in the denominator. So this is the term that will dominate when r becomes very large. So we're left with 1 over r d by d over r to the a theta in the phi hat direction, which becomes negative mu naught p naught omega squared over 4 pi c sine theta over r cosine omega t minus rc in the phi hat direction. That should look familiar, because the E field and the B field look almost exactly alike. The only difference is the B is 1 over c times the factor of the E field, and the B field is pointing in the phi hat direction. Which way does phi hat points? Phi hat points east. So you're standing on the surface of the Earth, you're going to feel an electric force pulling you north, you're going to feel a magnetic field pointing to the east. And this should strike you as a wave equation. The B field and the E field are exactly alike, except they're perpendicular. The B field is 1 over c times the E field, and otherwise they're exactly in sync. This is actually a spherical wave that starts at the origin of a sphere and extends outwards. It decays with the 1 over r, so the further you get away, the weaker it gets. It doesn't change its phase or its frequency. The phase is only changed based on the distance you are from the center, and otherwise it's a pretty straightforward, field. Of note, if you want to increase the strength of the fields, you have to increase the strength of omega. You're going to get a much more bang for the buck for your doubling of the omega versus doubling of the charge or the distance between them. So let's calculate the pointing vector now. So the pointing vector is just 1 over mu naught E cross B. E and B have the same magnitude except for that factor of C. So we just get rid of one of the mu naughts. So we have 1 mu naught, we have 2 p naughts, we have 4 omegas, and then we have 4 pi squared, which is 16 pi squared, and then the factor of C coming from the B field. Sine theta over r is squared, and we have cosine squared omega t minus rc. Taking the average of that to find the intensity, well, basically the only thing that's going to change is this cosine, and we know that the average of cosine squared is just 1/2. So we get another factor of 2 in the denominator, and it's still pointing the r hat direction. Mu naught p naught squared omega to the 4th over 32 pi squared c sine theta over r squared in the r hat direction, so it's pointing away. This says the energy is being directed away from the center. The energy increases according to the square of the dipole moment, but according to the 4th power of omega. So if you double the frequency, you get 16 times as much power being emanated. But if you only double the dipole moment, then you only get 4 times as much power leaving the center there. The total power emitted is found by the integral of S over the surface of a sphere with radius r centered on the dipole. So we're going to take the average power emitted is going to be the average of the S vector all across the surface of a sphere. So obviously this factor can just fly out of there. Sine theta over r squared. Well, we have an r squared here. We have an r squared from the sphere, surface of a sphere integral. So these two cancel. So we're left with the sine cubed theta d theta d phi. And solving for that, it turns out the sine cubed theta d theta from 0 to pi is 4/3. I used Wolfram Alpha to look that up. You can probably look in your book if you don't want to use Wolfram Alpha. It'll actually walk you through various ways to do it. Substitution of variables, I think, is the one that they used, if I recall correctly. And finally, d phi goes from 0 to 2 pi, so it's just 2 pi. So we have an extra factor 2 pi that cancels out some of the 32, but definitely one of the pi's. We have a 3 in the denominator and a 4 in the numerator, so that's an airplane flying overhead right now. I hope you don't mind. And he's gone. I don't know if you guys heard that or not. So we have 4 times 2 is 8 divided by 32. We have 4 left over. 1 over 4 pi epsilon naught. It's our old familiar friend. We change the mu naught into epsilon naught c squared, so we have another 2 c's. 1 over 4 pi epsilon naught is a very common thing. We have p naught squared, omega to the 4th over 3 c to the 3rd power. So again, the total power is it doesn't depend on how far you are from the center because no power is being lost. It does show you that that factor p naught squared and the factor of omega to the 4th are still present. Increasing the frequency dramatically increases the power. Finally, here's some notes on how this relates to why the sky is blue. And to kind of back this up, I think it was 3 different times in my physics education where they explained why the sky is blue. Once was in the introductory physics course, once in the electromagnetism, which is what we're doing right now, and the other time in quantum mechanics. In this case, if you think about it, you're standing on the surface of the Earth and looking up, and the sun is shining across the sky. Light from the sun will cause the molecules in the atmosphere to behave like an oscillating electric dipole. And if you think about, you remember the E and the B fields, or let's just think about the E field actually. That's the one that's probably the most powerful in terms of making them then oscillate. So the E field is perpendicular to the direction of travel of light. And so that means that some of the light is going to be oscillating from your perspective up and down, and some of it's going to be oscillating towards and away from you. The one that's oscillating towards and away from you, because of that cosine theta, you won't be able to see any emission from that. Instead, the one that's oscillating up and down, so you're looking at it at the perpendicular, those are going to give you the maximum intensity. And also we note that if you're looking down, so if the light's shining towards you, then in no case will any of those oscillations, the oscillations will be maximized. The radiation from the oscillation will be maximized because you're always looking at the perpendicular to the oscillations. So you're really not losing anything or gaining anything. So blue light, the higher omega, will radiate much more intensely than red light, lower omega. So that means that the light you see from the side will be much more intense from blue than from red. But if you're looking straight down towards the sky, or towards the sun, then you will see reddish light because some of the blue light has been basically diverted to the side. That's why the sky is blue. So if your kid asks, why is the sky blue? You say, well, it's because the average intensity of the pointing vector is mu naught p naught squared omega to the 4th over 32 pi squared c sine theta over r squared in the r hat direction for a oscillating dipole. So thanks for watching. Be sure to subscribe, like, comment, and share. Let me know what you think about this new format. If you want me to try something else, or if you have any ideas, I'd appreciate that. And thanks to all for your subscriptions and continued support throughout the years. So take care. Bye-bye.